This is Chapter 12 homework for Physics 102A, starting with number 38. Here we have a 246-meter tall skyscraper with a steel frame, and we want to know how much does the building's height change between negative 20 degrees Celsius and 40 degrees Celsius. So we use alpha, the coefficient of length expansion for steel, 1.2 times 10 to the negative 5 degrees Celsius, or per degree Celsius. Change in length is original length, 246 meters, times alpha times delta t. In this case, it doesn't really matter based on the wording of the question whether we do final or initial 40 degrees Celsius or negative 20 degrees Celsius. Just do one or the other. Depending on which way you do it, you'll get a positive or a negative answer. I chose the way that would make it give a positive answer. The point is, the difference in temperature between the hot and cold extremes is 60 Celsius degrees. So when we plug that in, we get a change in length of 0.177 meters. So this 246 meter skyscraper changes in length by 17.7 centimeters. Number 44, 99.8 milliliters of ethanol will exceed 100 milliliters at what temperature? That's what it means by overflowing the 100 milliliter beaker. Now this problem is made a little easier in that we don't have to take into account the expansion of the beaker. Practically speaking, we would, but the problem says to ignore that. So it's asking, at what temperature, or what temperature change, would 99.8 milliliters of ethanol become, or exceed 100 milliliters? So we can say, well, first we look for beta, the coefficient of volume expansion for ethanol, 7.5 times 10 to the negative 4 per Celsius degree. Change in, I'm sorry, this is a mistake. This should be volume. Volume. Actually, all my L's here should be volumes. Very sorry about this. Doing this left-handed. Okay, sorry about that. Change in volume is original volume times beta delta t. Solving algebraically for delta t, change in temperature, we get change in volume times, again, V naught original volume over beta. Change in volume is 0.2 milliliters. Original volume is 99.8 milliliters. Coefficient of expansion is 7.5 times 10 to the negative 4. Whatever units I use, whether I keep it in milliliters, whether I choose to convert it to MKS, it doesn't matter. As long as they're the same unit, those units are going to divide out. And what we're left with is 1 over per degree Celsius. So the units become Celsius degrees. So we get change in temperature is 2.67 Celsius degrees. Now, we want to know what the actual temperature is. So remember, change in temperature is final minus initial. So we call that T minus T naught. And we want to solve for T. Add T naught to both sides of this equation. And we get T equals T naught plus 2.67 Celsius degrees. 25 degrees Celsius plus 2.67. The temperature at which the ethanol will overflow is 27.67 degrees Celsius. Next is number 49. 4 questions. First of all, part A. We're looking at 1 mole of argon. It's important here to know that argon, if you look on a periodic table, it's on the right-hand column among the inert gases. So you know that argon does not form into molecules. It's monatomic. So we don't have to worry about having 1, 2, or 3 atoms like we do H2 or O2 or N2. It's just 1 atom of argon. And on the periodic table, we see its molecular mass is 39.95. In class, I told you can round that to 40. But in this case, we can be more precise and just go with 39.95. Close enough to 40, though. What this tells us, what that number means, is that 1 mole has a mass of 39.95 grams. Part B asks about a 1/4 mole of carbon dioxide. So first we count up the molecular mass. We have a carbon and 2 oxygens, so 12 plus 16 plus 16. You can be more precise and use the exact number given in the periodic table, but it'll come out pretty close to 44. Now what that means is, right here, 44 grams per mole of carbon dioxide. We're dealing with a 1/4 of that, so a 1/4 of a mole times 44 grams per mole gives a mass of 11 grams. Part C, we're dealing with another inert gas along the right-hand column of the periodic table. 2.6 moles of neon. So being an inert or a noble gas, it's monatomic. We look on the periodic table, its mass is 20.18. The examples I did in class, like carbon, where I said it's pretty close to 12, or oxygen, pretty close to 16, even argon in part A, pretty close to 40. Here, it's not so much pretty close. Rounding this down to 20 will bring you off a bit, so let's go with the 20.18, especially in this case. 2.6 moles times 20.18 grams per mole gives us 52.47 grams. And for D, we're dealing with uranium hexafluoride. We counted up. The mass of uranium is 238, plus 6 times fluorine, which is about 19, and we get 352 grams per mole. Again, if you want to be more precise, use the more precise numbers given in the periodic table. 1.5 moles times 352 grams per mole gives us 528 grams of uranium hexafluoride. Number 51. Estimate how many air molecules are in a room measuring 8 meters by 7 meters by 2.8 meters. Well, what's good to know is figuring out that volume of the room would be 156.8 cubic meters. The pressure, it says assume 1 atmosphere, so that's 1.013 times 10 to the 5th pascals. And the temperature, 22 degrees Celsius, let's call that 294 Kelvin. Since the question is asking how many molecules, I have a choice between PV equals nRT and PV equals nKT. Let's use the one that uses the capital N, the big N, meaning number of molecules. Solving it algebraically for n, we get n equals PV over KT. We've already solved for all of those. So plugging in those numbers, we get 3.9 times 10 to the 27 molecules, roughly. Number 53. A spherical balloon with radius 10 centimeters. It'll be useful first to find the volume. If it's a sphere, that's 4/3 pi r cubed. So the radius r is 0.1 meters. And there we have its volume, 0.004 meters cubed. It says it's at an original pressure of 1.05 atmospheres. Here I convert it to pascals. 1.064 times 10 to the 5th pascals. Then the pressure is increased to 1.75 atmospheres. Let's get that in pascals as well. 1.773 times 10 to the 5th pascals. Part A is asking, does the balloon size increase or decrease? Now, we could do part B to come up with that answer, but let's do this conceptually. With PV equals nRT, everything that's constant is to the right-hand side. Everything that varies is to the left. So it doesn't matter to me at the moment what is on the right-hand side. The point is that that right-hand side is constant, meaning the left-hand side, P times V, is some constant number. So if pressure increases, and pressure times volume is constant, there's this inverse relationship between pressure and volume. So if pressure increases, volume must decrease. Now, let's solve for it. Here's the trick. When you have PV equals nRT, isolate on one side of the equation, on the right-hand side, the things that are constant, and on the left-hand side, the things that vary. In this case, it's already in that form. PV, there's the things that vary, equals nRT. I'm going to change that. I'm going to cover up this nRT and just say PV equals constant. I don't really care what that constant is, just to know that P times V is constant. And if it's constant, then I can say P0 times V0 equals P1 times V1. I want to know what the final volume is, V1. So solving this equation for V1, we get volume 1 equals volume 0 times the ratio of P0 over P1. Instead of solving for the volumes and then solving for the radii, here's something neat to do. Substitute in place of V1, call it 4/3 pi R1 cubed. That's a cubed right there. And in place of V0, excuse me, substitute 4/3 pi R0 cubed. So the 4/3 and the pi will divide out of both sides of the equation. What we're left with is that R1 cubed, look at this here, this line I'm pointing at, but get rid of this 4/3 pi and this 4/3 pi. They just divided out. What you're left with is R1 cubed equals R0 cubed times P0 over P1. If we want to solve for R1, meaning the final radius, take the cube root of both sides. So R1 equals R0 times the cube root of P0 over P1. Plugging in the numbers, we get 10 centimeters times the ratio, 1.05 atmospheres over 1.75 atmosphere, and cube root it. So what we get is the final radius of 8.43 centimeters. Number 54, closed flask, temperature at 298 Kelvin, pressure at 1 atmosphere. What is the new temperature when the pressure is changed to 1.65 atmospheres? The trick I showed in problem number 53. Take PV equals nRT, but isolate to the left-hand side the things that vary, and to the right-hand side the things that are constant. So P over T equals nR over V. P over T is equal to some constant. So let's just focus on that. If P over T is constant, then we have P0 over T0 equals P1 over T1. And if we want to solve that algebraically for T1, T1 becomes P1 over P0 times T0. Now we plug in the values. So T1 equals P1, 1.65 atmospheres over 1 atmosphere, times T0, 298 Kelvin, which gives us T1 is 491.7 Kelvin. Now it's proper form to give your answer in the form that the question was asked. It's polite to do that. So since the temperature was given in the problem in degrees Celsius, we should give the answer in degrees Celsius. So let's subtract 273 from 491.7 Kelvin, and we get the final temperature of 219 degrees Celsius.